The Andromeda Galaxy is visible from your backyard. You can see it with binoculars. That tiny smudge of light represents a distance so vast, so incomprehensible, that the human brain literally cannot process it. But we're going to try anyway. And one quick question. If you could rewrite one law of physics, which would you change, and how would it transform the universe? Let me know in the comments. I will pin the most creative answer. Now let's begin. Andromeda sits roughly 2.5 million light-years away from us. To put that in perspective, 1 light-year is the distance light travels in a single year, moving at approximately 186,000 miles per second. That's about 5.88 trillion miles in 1 year. Now multiply that by 2.5 million. The numbers become so enormous they stop having meaning to our everyday brains. We're talking about distances that dwarf anything we've ever encountered in our solar system. Scientists have known about Andromeda for centuries. The Persian astronomer Al-Sufi mentioned it as early as 965 CE in his Book of the Fixed Stars, describing it as a small cloud. In 1612, shortly after the telescope was invented, German astronomer Simon Marius observed it more closely, saying it resembled the light of a candle seen through horn. For a long time, astronomers thought Andromeda was just another nebula, a glowing cloud of gas within our own Milky Way. But everything changed in the 1920s. Edwin Hubble, using the massive 100-inch telescope at Mount Wilson Observatory, made a discovery that revolutionized our understanding of the cosmos. He identified individual stars within Andromeda, including Cepheid variables, stars that pulse with predictable rhythms. By measuring how these stars brightened and dimmed, Hubble calculated their true brightness, and from that, their distance. The result shocked the astronomical community. Andromeda wasn't part of the Milky Way at all. It was an entirely separate galaxy, unimaginably far away. Overnight, the known universe expanded from one galaxy to billions. Today, thanks to missions like the Hubble Space Telescope and the Gaia Observatory, we know even more about Andromeda. It's not just sitting out there peacefully, it's moving. Gaia's data from 2024 reveals that Andromeda is heading toward us at roughly 68 miles per second. Don't panic though. In about 4 billion years, our two galaxies will collide. But collide is a misleading word. The stars are so far apart that very few will actually crash into each other. Instead, gravitational forces will pull and twist both galaxies, eventually merging them into one giant elliptical galaxy that astronomers playfully call Milkomeda. But let's get back to your hypothetical journey. You're sitting in your spacecraft, engines ready, destination locked, Andromeda. The first question you need to ask is, how fast can we go? Right now, the fastest human-made object is the Parker Solar Probe, which reached speeds of approximately 430,000 miles per hour as it dove close to the Sun. That sounds incredibly fast until you realize it's only about 0.06% of the speed of light. At that speed, reaching Andromeda would take over 4 billion years. You'd need something far, far faster. Let's imagine we somehow developed a spacecraft that could travel at 10% the speed of light. That's still a staggering achievement, requiring technologies we don't yet possess. At 10% light speed, your journey to Andromeda would take 25 million years. You'd need generation after generation of humans to be born, live, and die aboard that ship. The people who arrived wouldn't remember Earth except through stories passed down over thousands of generations. Even the constellations they'd see from their windows would shift and change as the ship crossed unimaginable gulfs of space. What if we pushed harder? What if we could reach 50% the speed of light? Now we're talking about 5 million years. Still far beyond any human lifespan, but we're getting closer to something conceptually graspable. However, at these speeds, physics starts behaving strangely. Einstein's theory of special relativity tells us that as you approach the speed of light, time itself begins to slow down for you relative to everyone else. This phenomenon, called time dilation, means that while millions of years pass on Earth, far less time might pass for you aboard the ship. If you're still watching and finding this journey as fascinating as I do, take a moment to subscribe and hit that thumbs up button. It really helps this channel grow and allows me to keep exploring these cosmic mysteries with you. Here's where things get truly mind-bending. Let's say you manage to accelerate to 99% the speed of light. From Earth's perspective, your trip to Andromeda would still take about 2.5 million years, but on board your ship, due to time dilation, only about 35,000 years would pass. That's still longer than recorded human history, but it's a fraction of what outside observers would measure. Push even closer to light speed, say 99.99%, and your onboard clocks might measure only a few thousand years. The universe outside your windows would age millions of years while you experience just millennia. But here's the catch: you can never actually reach the speed of light. According to Einstein, as you accelerate closer and closer to light speed, your mass effectively increases, requiring more and more energy to go faster. To reach exactly the speed of light would require infinite energy, which is impossible. Light itself can travel at that speed because photons have no mass. You, your ship, every atom aboard, all have mass, and that means you're forever stuck just below that cosmic speed limit. Even if we ignore that limitation for a moment, traveling at near-light speeds introduces other terrifying challenges. Space isn't empty. It's filled with hydrogen atoms, dust particles, and cosmic radiation. At normal speeds, these pose little threat. But at 99% light speed, every speck of dust becomes a deadly projectile. A single hydrogen atom hitting your ship at that velocity would impact with the force of a bomb. You'd need shielding so advanced we can barely imagine it. Some scientists have proposed using powerful magnetic fields to deflect charged particles or layers of expendable material at the front of the ship to absorb impacts, but we're still in the realm of theoretical speculation. Then there's the energy problem. How do you power a ship to such incredible speeds? Chemical rockets, the kind we use today, are laughably inadequate. The most efficient rocket fuel we have would require more mass than exists in the observable universe to accelerate a small ship to even a fraction of light speed. We'd need something entirely different. Nuclear fusion, where hydrogen atoms fuse into helium and release tremendous energy, is one possibility. It powers the sun and could theoretically power a spacecraft, but we haven't yet built a working fusion reactor for Earth, let alone a starship. Another idea is antimatter propulsion. When matter and antimatter meet, they annihilate each other, converting 100% of their mass into pure energy. This is the most efficient energy source we know of. Just a few grams of antimatter could power a city for years. But producing antimatter is incredibly difficult and expensive. Right now, we can only create tiny amounts in particle accelerators, and storing it without letting it touch normal matter and explode is an engineering nightmare. Building an antimatter engine capable of accelerating a ship to near-light speeds remains firmly in the realm of science fiction, at least for now. Some scientists have proposed even more exotic solutions. The concept of a light sail, for instance, involves using enormous mirrors or sails pushed by laser beams or sunlight. In 2016, physicist Stephen Hawking and entrepreneur Yuri Milner announced the Breakthrough Starshot initiative, which aims to send tiny, gram-scale probes to our nearest star system, Alpha Centauri, using powerful Earth-based lasers to push light sails to 20% light speed. If successful, those probes could reach Alpha Centauri in about 20 years. But scaling that technology to carry humans across millions of light years to Andromeda, that's a problem of an entirely different magnitude. Let's talk about what you'd actually see if you somehow survived the acceleration and were cruising toward Andromeda at near light speed. the view would be utterly alien. Due to an effect called relativistic aberration, the stars ahead of you would appear to shift and bunch together, creating a bright ring of light directly in front of your ship. Meanwhile, the stars behind you would dim and redshift, their light stretching into longer, redder wavelengths. If you were traveling fast enough, the stars ahead would blue shift so dramatically they'd emit X-rays and gamma rays. You'd be flying into a wall of deadly radiation created simply by your own speed. The Milky Way behind you would gradually shrink, becoming just another point of light among billions. For the first few hundred years of your journey, assuming you could survive that long, you'd be in intergalactic space, the vast emptiness between galaxies. This is the loneliest place in the universe. The nearest stars would be thousands of light years away in any direction. If you looked back at the Milky Way and forward toward Andromeda, you'd see two islands of light separated by an ocean of darkness. No planets, no stars, no sun to warm you, just the endless void. This intergalactic void isn't completely empty, though. It contains thin wisps of hydrogen gas, dark matter we can't see but know exists through its gravitational effects, and the cosmic microwave background radiation, the afterglow of the Big Bang itself. This faint radiation fills all of space, a whisper from the universe's birth 13.8 billion years ago. As you traveled, you'd be swimming through this ancient light, and due to your speed, you'd see it blue shifted in front of you and red shifted behind you, creating a strange cosmic glow. Speaking of time, let's consider what's happening back on Earth while you're journeying to Andromeda. If you left today at 99.99% light speed and your onboard clocks measured, say, 10,000 years passing, more than 2.5 million years would have elapsed on Earth. Every human you knew would be long dead. Civilizations would rise and fall, species would evolve and go extinct, the continents would drift into new configurations. When you finally arrived at Andromeda and looked back toward the Milky Way, the Earth you left wouldn't exist anymore, at least not in any form you'd recognize. This brings up one of the most profound aspects of near-light-speed travel. It's essentially a one-way ticket into the future. You can never go back to the time you left. Even if you turned around immediately and returned to Earth at the same speed, millions more years would have passed. You'd become a time traveler, but only forward, never backward. This isn't science fiction. It's a direct consequence of Einstein's relativity, confirmed by countless experiments. Atomic clocks flown on jets run slower than identical clocks on the ground. GPS satellites have to account for time dilation, or their positioning would be off by miles. The physics is real and tested. Now you might wonder, couldn't we just go faster? What about wormholes or warp drives, the kind of technology we see in science fiction? These ideas aren't completely crazy. Einstein's general theory of relativity, which describes gravity as the curvature of space-time, does allow for some exotic solutions. A wormhole is essentially a tunnel through space-time connecting two distant points. If you could create and stabilize a wormhole, you could theoretically step through one end near Earth and emerge instantly near Andromeda, bypassing the normal constraints of distance and speed. But here's the problem. We've never observed a wormhole, and creating one would require something called exotic matter, a substance with negative energy density. We've never found exotic matter, and it might not even exist. Even if it does, the amounts needed to hold open a wormhole large enough for a spaceship would be enormous, possibly more than exists in the entire universe. Most physicists consider traversable wormholes to be theoretically possible, but practically impossible with anything resembling our current understanding of physics. Then there's the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. The idea is to contract space-time in front of your ship and expand it behind you, creating a warp bubble that carries you faster than light without actually moving through space at all. You'd be surfing on a wave of space-time itself. It's a beautiful concept and mathematically consistent with general relativity, but again it requires exotic matter with negative energy, and the energy requirements are staggering. Early calculations suggested you'd need the energy mass equivalent of the entire observable universe. More recent refinements have reduced that somewhat, but we're still talking about energy scales far beyond anything humanity can produce. If you're interested in learning more about the challenges of interstellar travel and what it would take to reach even our closest stellar neighbor, I recently made a video called The Terrifying Journey to Alpha Centauri. Out as that star system is only 4.3 light-years away, yet the obstacles are immense. Check it out after this video. The link is in the description and on the card above. Now let's assume for a moment that we solve all these impossible problems. You've got your near-light-speed ship, your shielding against interstellar dust, your fusion or antimatter engines, and enough resources to sustain you for the subjective years or decades the journey might take from your perspective. You're finally approaching Andromeda. What would you see? First, Andromeda would grow from a faint smudge to a magnificent spiral dominating your sky. Unlike our view from Earth, where we see Andromeda edge on as an elongated blur, you'd see it in all its glory. Two prominent spiral arms swirl outward from a bright central bulge. The galaxy spans roughly 220,000 light-years across, making it slightly larger than our Milky Way. Over 1 trillion stars populate this cosmic city, compared to our galaxy's estimated 200 to 400 billion. As you drew closer, individual stars would become visible, then nebulae, vast clouds of gas and dust where new stars are being born. Andromeda isn't alone. It has at least 14 satellite galaxies orbiting it, smaller dwarf galaxies held in gravitational thrall, much like the Magellanic Clouds orbit the Milky Way. Two of the largest, Messier 32 and Messier 110, are clearly visible even from Earth through modest telescopes. As you approached, you'd see these smaller galaxies scattered around Andromeda like moons around a planet, each one containing millions or billions of stars. The core of Andromeda is a fascinating and terrifying place. Recent observations from the Hubble Space Telescope and other instruments suggest that at the very center lies a supermassive black hole weighing in at roughly 140 million times the mass of our Sun. That's significantly more massive than Sagittarius A star, the supermassive black hole at the heart of the Milky Way, which is about 4 million solar masses. This central black hole doesn't just sit there passively. It warps space-time around it so severely that nothing, not even light, can escape once it crosses the event horizon. As you navigated into the outer regions of Andromeda, you'd need to choose your destination carefully. The galaxy contains regions of intense star formation, where massive young stars blaze with blue-white light, as well as older, quieter neighborhoods dominated by red and yellow stars like our Sun. You'd want to avoid the core, where stars are packed so densely that gravitational interactions could fling you off course or into dangerous radiation zones. Instead, you might head for one of the spiral arms, where the density is more manageable and the scenery spectacular. But here's something that should give you pause. We don't actually know if Andromeda has planets like Earth. We've discovered thousands of exoplanets in our own galaxy using techniques like the transit method, where a planet passing in front of its star causes a tiny dip in brightness. But Andromeda is so far away that even our most powerful telescopes can't detect individual planets there. We assume they exist because planet formation seems to be a natural byproduct of star formation, but we can't confirm it. You might travel 2.5 million light-years only to find that habitable worlds are rare or non-existent in your target region. Let's zoom out for a moment and consider the bigger picture. Andromeda and the Milky Way are part of what astronomers call the local group, a collection of over 50 galaxies bound together by gravity. Most are small dwarf galaxies, but Andromeda and the Milky Way are the two giants, the dominant members. The entire local group spans about 10 million light-years across. Beyond that lies the Virgo supercluster, a much larger structure containing thousands of galaxies, and our local group sits on its outer edge. These structures remind us of something profound. We're not isolated. The universe is organized in a cosmic web, with galaxies clustering into groups, groups into clusters, and clusters into superclusters, all connected by filaments of dark matter and separated by vast voids where almost nothing exists. Andromeda isn't just a random destination. It's our closest major neighbor in this grand cosmic architecture, a sibling galaxy sharing the same corner of the universe. One of the most humbling aspects of contemplating a journey to Andromeda is confronting the sheer scale of time and space. Our lives are so brief. A human lifetime is, at best, about 100 years. Recorded human history spans roughly 5,000 years. Our species, Homo sapiens, has existed for maybe 300,000 years. The universe is 13.8 billion years old. On cosmic timescales, we're barely a blip. And yet here we are, conscious beings capable of understanding the universe, measuring distances to galaxies, and dreaming of journeys across the void. There's a beautiful paradox in this. We're made of atoms forged in the hearts of dying stars. The carbon in your bones, the iron in your blood, the oxygen you breathe, all were created in stellar furnaces billions of years ago. When those stars exhausted their fuel and exploded as supernovae, they scattered these elements across space. Eventually, they coalesced into new stars, planets, and, on at least one world we know of, life. You are, quite literally, stardust given form and consciousness. And now that stardust is contemplating a journey back to the stars, to another galaxy, to see what else the universe has created. Let's talk about what it would actually take to keep humans alive during a journey to Andromeda. Even if we solve the propulsion problem, even if we somehow reach near light speeds, we still have to deal with biology. Human bodies weren't designed for space travel, let alone journeys lasting thousands or millions of years. We evolved under Earth's gravity, breathing Earth's atmosphere, eating Earth's food. Take us away from those conditions and problems start appearing fast. First, there's radiation. On Earth, we're protected by our planet's magnetic field and atmosphere, which deflect and absorb most cosmic rays and solar radiation. In deep space, especially intergalactic space, you'd be exposed to galactic cosmic rays, high-energy particles traveling at nearly light speed, originating from supernovae and other violent cosmic events. These particles can pass right through spacecraft hulls and human tissue, damaging DNA and increasing cancer risk. Long-term exposure could be lethal. The solution? You'd need serious shielding. Water is actually pretty good at blocking radiation, so some designs propose surrounding living quarters with tanks of water or other hydrogen-rich materials. Alternatively, you could use powerful magnetic fields to create an artificial magnetosphere around your ship, deflecting charged particles just like Earth's magnetic field does. But generating a field strong enough to protect an entire spacecraft would require enormous amounts of energy you'd need to sustain for the entire journey. Then there's the problem of resources. Humans need food, water, and breathable air. You can't pack millions of years' worth of supplies even for a small crew. You'd need a completely closed-loop life support system, recycling everything. Your waste becomes fertilizer for plants. Plants produce oxygen and food. Water is endlessly purified and reused. The International Space Station already does this to some extent, but it's not perfect. They still need regular resupply missions from Earth. On a journey to Andromeda, there are no resupply missions. Every system has to work flawlessly for as long as the journey takes. Some scientists have proposed generation ships, massive vessels large enough to sustain entire communities. The idea is that the people who leave Earth wouldn't be the ones who arrive at Andromeda. Instead, generations would be born, live, and die aboard the ship. You'd need to maintain genetic diversity to avoid inbreeding, so the initial population would need to be at least several hundred people, maybe thousands. You'd need farms, schools, hospitals, everything a society needs, and you'd need to ensure that culture and knowledge are preserved across countless generations. But here's a psychological challenge that's harder to quantify. Would people born on the ship even care about the mission? Imagine you're born in a metal tube floating through the void. You've never seen Earth. You've never felt rain or breathed fresh air. Your parents, grandparents, great-grandparents for hundreds of generations were all born on this ship. Andromeda is still thousands of years away. Would you maintain the mission, or would you question why your ancestors condemned you to this existence? Maintaining motivation and purpose across such timescales might be the hardest challenge of all. Another option is suspended animation or cryogenic freezing. If we could safely put humans into a state of hibernation, slowing or stopping biological processes, the subjective experience of the journey would be much shorter. You'd go to sleep near Earth and wake up near Andromeda with no memory of the time in between. But here's the problem. We can't do this yet. We can freeze human cells, embryos, even some small organisms, but freezing and reviving a whole human without causing fatal damage is beyond our current capabilities. Ice crystals form inside cells, rupturing them. Metabolic processes don't just pause, they stop, and restarting them is incredibly complex. Some researchers are exploring alternatives like induced torpor, a hibernation-like state that doesn't involve freezing. Bears and other animals do this naturally, slowing their metabolism to survive winter. If we could induce something similar in humans, it might work. But even if we perfect the technique, you'd still need automated systems to maintain the ship, navigate hazards, and wake the crew when necessary. And what if something goes wrong while everyone's asleep? Who fixes it? There's also the option of sending robots or artificial intelligence instead of humans. Machines don't need air, food, or water. They don't suffer from radiation the same way biological organisms do. They can be designed to function for centuries or longer. We've already sent robotic probes to every planet in our solar system and beyond. Voyager 1 and Voyager 2, launched in 1977, are still sending data back from interstellar space over 45 years later. A sufficiently advanced probe could, in theory, make the journey to Andromeda, collect data, and send it back to Earth. But even that has limitations. Radio signals travel at the speed of light, so any message from a probe at Andromeda would take 2.5 million years to reach us. By the time we received the data, humanity might not even exist anymore, at least not in any form we'd recognize today. And there's something fundamentally different about sending machines versus going ourselves. A robot can't experience wonder. It can't look at the stars and feel the awe that we feel. It can measure and catalogue, but it can't truly understand. Let's consider an even more radical idea. What if we didn't send our biological bodies at all? What if we uploaded our consciousness into machines or digital substrates? This is the realm of speculative futurism, but some scientists take it seriously. If consciousness is ultimately a product of brain processes, patterns of neurons firing in particular ways, then theoretically, those patterns could be replicated in silicon or some other medium. You'd transfer your mind into a computer, and that digital copy of you could pilot a spacecraft to Andromeda without worrying about food, air, or radiation. Of course, this raises profound philosophical questions. Is a digital copy of you really you? If your biological body dies but the upload survives, are you still alive, or is it just a simulation that thinks it's you? Different philosophers have different answers. But from a practical standpoint, if it worked, It would solve many of the challenges of long-duration space travel. A digital consciousness doesn't age. It doesn't need to eat. It could potentially experience time differently, speeding up or slowing down its subjective experience as needed. Now let's think about what you'd learn if you actually made it to Andromeda. Scientists believe that Andromeda formed roughly 10 billion years ago, a few billion years after the Big Bang. It's had a violent history. Observations suggest it's cannibalized several smaller galaxies over time, absorbing them and growing larger. The Hubble Space Telescope's survey of Andromeda, completed in 2025, revealed that the galaxy has experienced multiple bursts of star formation, periods where enormous numbers of stars were born in relatively short spans of time, astronomically speaking. These bursts were likely triggered by collisions with other galaxies. When galaxies collide, their gas clouds slam together, compressing and heating the gas, triggering waves of new star formation. Some of the stars in Andromeda are ancient, nearly as old as the universe itself, while others are young, born just a few million years ago. This mix gives the galaxy a complex structure, layers upon layers of stellar populations, each telling part of the story of cosmic evolution. At the center of Andromeda, as I mentioned earlier, lurks a supermassive black hole. But recent studies suggest it might actually be two black holes orbiting each other at the galaxy's heart. If true, this would be the result of a past galactic merger, where Andromeda swallowed another galaxy, and the two central black holes eventually sank to the core and began their gravitational dance. Someday, millions or billions of years from now, they'll spiral closer and closer until they merge in a cataclysmic event, releasing gravitational waves that will ripple across the universe. Gravitational waves are distortions in space-time itself, predicted by Einstein and first directly detected in 2015 by the LIGO Observatory. When two massive objects like black holes merge, they shake the fabric of space, and those ripples spread outward at the speed of light. If Andromeda's central black holes merge while you're there, you could potentially detect those waves, witnessing one of the universe's most violent events. Of course, you'd want to be very far from the core when it happens, because the energy released would be staggering. Andromeda also contains globular clusters, dense, spherical collections of stars that orbit the galaxy. Some of these clusters contain hundreds of thousands or even millions of stars packed into regions just a few dozen light-years across. If you visited one, the night sky would be breathtaking. Stars would be so close together that some nights would never truly be dark. Shadows would shift as multiple suns moved across the sky. But the gravitational interactions in such a dense environment would make stable planetary orbits difficult. Life, if it exists in globular clusters, would face unique challenges. One of the most exciting possibilities is that Andromeda might harbor life. With over 1 trillion stars and likely trillions of planets, the odds seem favorable. We don't know what percentage of planets are habitable or what percentage of habitable planets actually develop life, but even if the numbers are tiny, the sheer scale suggests that somewhere in Andromeda, life could exist. It might be microbial, simple organisms clinging to existence in extreme environments, or it might be complex, intelligent, technological civilizations building their own telescopes and wondering if they're alone in the universe. The question of extraterrestrial life is one of the most profound in science. Are we alone, or is life common? If you traveled to Andromeda and found even a single microbe, it would transform our understanding of biology and our place in the cosmos. It would tell us that life isn't a unique fluke confined to Earth, but a universal phenomenon arising wherever conditions allow. And if you found intelligent life, civilizations with their own cultures, technologies, and histories, the implications would be even more staggering. But here's the sobering reality. Even if intelligent life exists in Andromeda, we might never know. The distances are so vast and the timescales so long that communication would be nearly impossible. A radio signal sent from Andromeda would take 2.5 million years to reach Earth. By the time we received it and sent a reply, another 2.5 million years would pass. Any conversation would span epochs. Civilizations could rise and fall in the time it takes to exchange a single message. This is why some scientists focus on searching for techno-signatures, evidence of advanced technology that might be easier to detect than biological life itself. For example, a civilization advanced enough to harness the energy of their entire star, a concept called a Dyson sphere, would emit a distinctive infrared signature as waste heat. We haven't found any such signatures in Andromeda yet, but our searches are still in their infancy. Absence of evidence isn't evidence of absence, as the saying goes. There's also the possibility that life in Andromeda is so different from Earth life that we wouldn't recognize it. Life as we know it is based on carbon chemistry and liquid water, but could life exist using different chemistry, perhaps silicon instead of carbon, or ammonia instead of water? Could there be forms of life that don't even rely on chemistry at all, perhaps electromagnetic or plasma-based organisms? If such exotic life exists, our current detection methods might completely miss it. Thinking about all these possibilities reminds us of something Carl Sagan once said: "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." Our journey to Andromeda, even if only hypothetical, is part of that self-discovery. It's the universe, through us, reaching out to understand its own structure, its own history, its own possibilities. Before we continue deeper into this journey, let's pause and consider the astronomical tools that have allowed us to learn so much about Andromeda without ever leaving Earth. Our knowledge of this distant galaxy comes from centuries of patient observation, from the first telescopic glimpses to today's space-based observatories. Each technological leap has revealed new layers of detail, transforming that faint smudge in the sky into a rich, complex world we can almost imagine visiting. The Hubble Space Telescope, launched in 1990, revolutionized our view of Andromeda. Between 2010 and 2013, Hubble captured over 7,000 images of the galaxy, which astronomers painstakingly assembled into the largest and most detailed photograph ever taken of Andromeda. This mosaic contains over 100 million stars individually resolved. When you zoom into different regions, you can see star clusters, nebulae where new stars are forming, and lanes of dust threading through the spiral arms. It's a portrait of stunning beauty and scientific value. More recently, the James Webb Space Telescope, which began operations in 2022, has turned its infrared eye toward Andromeda. Infrared light penetrates dust clouds that block visible light, revealing hidden regions of star formation. Webb can see cooler objects that Hubble missed, including brown dwarfs, failed stars that never quite ignited fusion, and the cold dust grains that will someday coalesce into new planetary systems. Each observation adds another piece to the puzzle of how galaxies form, evolve, and eventually die. Ground-based telescopes contribute too. The Keck Observatory in Hawaii, with its 10-meter mirrors, can measure the velocities of stars and gas clouds in Andromeda by analyzing how their light is Doppler shifted. Just like the pitch of a siren changes as an ambulance drives past you, light from objects moving toward us shifts toward blue wavelengths, while light from objects moving away shifts toward red. By mapping these velocities across Andromeda, astronomers can study how the galaxy rotates, how its spiral arms form, and how dark matter influences its motion. Dark matter is one of the great mysteries of modern cosmology. We can't see it directly because it doesn't emit, absorb, or reflect light. But we know it exists because of its gravitational effects. When astronomers measure how fast stars orbit in galaxies like Andromeda, they find that the stars are moving too fast. Based on the visible matter alone, the gravity shouldn't be strong enough to hold the galaxy together. The stars should fly apart, but they don't, which means there must be additional mass we can't see. We call this invisible component dark matter, and it makes up roughly 85% of all matter in the universe. Andromeda is embedded in a massive halo of dark matter extending far beyond its visible stars. This halo might stretch hundreds of thousands of light-years into space, dwarfing the galaxy itself. As you journey toward Andromeda, you'd actually enter its dark matter halo long before you reach the first stars. You wouldn't notice anything different, though. Dark matter particles interact so weakly with normal matter that trillions of them pass through your body every second without you feeling a thing. It's ghost matter, invisible and intangible, yet its gravity shapes the universe. Understanding dark matter is crucial for understanding cosmic structure. Computer simulations show that without dark matter, galaxies like Andromeda and the Milky Way couldn't have formed. The dark matter provided the gravitational scaffolding that allowed normal matter, hydrogen and helium gas, to collect and eventually form stars. In a very real sense, dark matter built the universe we see, even though we can't see the dark matter itself. Scientists around the world are conducting experiments to detect dark matter particles directly, but so far it remains elusive. Another invisible component shaping the universe is dark energy. While dark matter pulls things together through gravity, dark energy pushes things apart. Discovered in 1998, when astronomers observed that the expansion of the universe is accelerating, dark energy makes up roughly 68% of the total energy content of the cosmos. We don't know what it is. It might be a property of space itself, or it could be a new kind of energy field permeating everything. What we do know is that it's driving galaxies apart at an ever-increasing rate. This has profound implications for a journey to Andromeda. Right now, Andromeda is actually moving toward us, not away, because the local gravitational attraction between our two galaxies is stronger than the cosmic expansion, but galaxies beyond the local group are receding, and distant galaxies are moving away faster and faster. In the far future, billions of years from now, galaxies outside our local neighborhood will accelerate beyond the cosmic horizon, moving away so fast that light from them will never reach us. The universe will become a lonelier place, with isolated galaxy clusters separated by ever-growing voids. But let's return to your journey. Suppose you've crossed the intergalactic void and are now entering Andromeda's outer regions. The first stars you encounter would likely be part of the galaxy's stellar halo, a diffuse population of old stars orbiting far from the main disk. These stars are metal-poor, meaning they contain very few elements heavier than hydrogen and helium. They formed early in the galaxy's history, before generations of stars had lived and died, enriching the cosmos with carbon, oxygen, iron, and other heavy elements. These ancient stars tell us about Andromeda's youth. By studying their chemical composition and motion, astronomers can reconstruct the galaxy's early history, much like archaeologists piece together ancient civilizations from fragmentary evidence. Some halo stars move in orderly orbits aligned with the galaxy's disk, suggesting they formed in place. Others have chaotic, highly elliptical orbits, hinting that they were captured from smaller galaxies that Andromeda devoured long ago. Each star is a witness to billions of years of cosmic history. As you venture deeper, you'd encounter the disk, where most of Andromeda's stars reside. The disk is relatively thin, only a few thousand light-years thick, but over 200,000 light-years across. It's divided into regions based on stellar populations. The inner disk contains older stars, while the spiral arms are dominated by younger, hotter stars. These massive blue stars burn bright but die young, living only a few million years before exploding as supernovae. Their presence marks active star formation regions. Star formation happens in molecular clouds, dense regions of gas and dust, where temperatures drop low enough for molecules to form. These clouds can be enormous, containing enough material to birth thousands or even millions of stars. When a region becomes dense enough, gravity takes over, pulling material inward. As the cloud collapses, it heats up and spins faster, eventually forming a protostar surrounded by a rotating disk of material. Planets form from this disk, condensing from dust grains that stick together and grow. If you explored Andromeda's spiral arms, you'd find these stellar nurseries in abundance. Giant molecular clouds, some spanning hundreds of light years, would glow faintly in infrared light. Within them, protostars would be heating up, preparing to ignite fusion. Once a star begins fusing hydrogen into helium in its core, it enters the main sequence, the stable phase where it will spend most of its life. Our Sun has been on the main sequence for about 4.6 billion years and will remain there for another 5 billion, but not all stars are created equal. The mass of a star determines its fate. Low-mass stars, less than about half the Sun's mass, burn their fuel slowly and can live for trillions of years, far longer than the current age of the universe. These red dwarfs are the most common stars in Andromeda and everywhere else, but they're so dim we can barely see them even with powerful telescopes. Medium-mass stars like the Sun live billions of years before swelling into red giants, and then shedding their outer layers to become white dwarfs, dense remnants about the size of Earth. High-mass stars, those more than about 8 times the Sun's mass, live fast and die young. They burn through their nuclear fuel in just a few million years. When their cores run out of fuel, they can't support themselves against gravity anymore, and they collapse catastrophically. The result is a supernova, one of the brightest events in the universe. For a few weeks, a single exploding star can outshine an entire galaxy. The core, if massive enough, collapses into a neutron star or a black hole. Andromeda has experienced countless supernovae over its 10 billion-year history. Each one scattered heavy elements across space, enriching the interstellar medium. These elements eventually found their way into new stars and planets. Every atom of carbon, nitrogen, and oxygen in your body was forged in stars and scattered by supernovae. You are, quite literally, made from the ashes of dead stars in galaxies like Andromeda and the Milky Way. This connection runs deeper than metaphor. It's chemistry, physics, the very fabric of your existence. Imagine standing on a hypothetical planet in one of Andromeda's spiral arms, looking up at the night sky. What would you see? First, you'd see thousands of stars, far more than visible from Earth in most locations, because you'd be in a denser part of the galaxy. The Milky Way would be visible as a faint, elongated smudge, much like Andromeda appears from Earth. If you had a telescope, you could pick out individual features in the Milky Way, its spiral arms, its central bulge. You'd be looking at our home galaxy from the outside, seeing it as others see us. But the view would be even more spectacular in the other direction. Looking toward the center of Andromeda, you'd see a glowing core, a dense concentration of billions of stars. On a clear night, it might cast faint shadows. Nearby, depending on where exactly you were, you might see Messier 32 and Messier 110, Andromeda's satellite galaxies. They'd appear as bright smudges, much clearer than they do from Earth. And beyond them, if you looked carefully, you'd see thousands of other galaxies scattered across the sky, each one an island universe in its own right. This brings us to an important point about perspective. From Earth, we tend to think of ourselves as the center, the reference point from which we measure everything else. But the universe has no center. Every point is equally valid. An observer in Andromeda looking back at the Milky Way would see us as we see them, a distant spiral galaxy among billions. The laws of physics are the same everywhere, The stars in Andromeda fuse hydrogen into helium just like our Sun. Planets orbit their stars following the same gravitational equations. If life exists there, it evolved through the same basic principles of chemistry and natural selection. This universality is one of the most profound insights of modern science. Despite the vast distances, despite the diversity of environments, the universe operates on consistent principles. We can study distant galaxies and be confident that our understanding applies because the fundamental constants, the speed of light, the gravitational constant, the charge of an electron, appear to be the same everywhere. This allows us to decode the light from Andromeda and learn about its stars, its gas, its history, all from 2.5 million light-years away. Let's dive deeper into what would happen during the actual voyage across the intergalactic void between the Milky Way and Andromeda. This region, stretching for over 2 million light-years, is one of the emptiest places you could possibly travel. To give you perspective, the average density of matter in intergalactic space is about 1 atom per cubic meter. That's far more empty than the best vacuum we can create in laboratories on Earth. You'd be traveling through near-nothingness for an inconceivable amount of time. During this crossing, assuming you were traveling at a significant fraction of light speed, you'd experience something called the interstellar medium differently than we observe it from Earth. The interstellar medium is the gas and dust between stars, and while it's incredibly sparse by terrestrial standards, at high velocities it becomes a hazard. Even individual hydrogen atoms, when you're slamming into them at 99% of light speed, carry tremendous kinetic energy. The cumulative effect of billions of these collisions would heat your ship's forward shielding to extreme temperatures. Some physicists have calculated that at very high, relativistic speeds, the friction from the interstellar medium alone could vaporize conventional materials. You'd need shielding made from materials that don't exist yet, perhaps carbon nanotubes arranged in specific configurations, or maybe something even more exotic like programmable matter that can repair itself on the fly. Alternatively, you'd need that magnetic deflection system we discussed earlier, powerful enough to push particles out of your path before they impact your hull. There's another eerie aspect of intergalactic travel worth considering: the profound isolation. Once you're deep in the void between galaxies, you're farther from any star than almost anywhere else in the universe. If you looked out your windows, assuming you had conventional windows and not just sensor displays, you'd see the Milky Way behind you and Andromeda ahead, both appearing as small, distant smudges. Everything else would be darkness, punctuated by the faint glow of even more distant galaxies. There would be no nearby stars to navigate by, no sun to provide warmth or light. This darkness would be broken only by the cosmic microwave background, that faint afterglow of the Big Bang we mentioned earlier. From your perspective, due to your tremendous velocity, this background radiation would be dramatically blue-shifted in front of you and red-shifted behind you. In fact, at high enough speeds, the blue-shifted cosmic microwave background ahead could become intense enough to be dangerous, bombarding your ship with high-energy photons. You'd essentially be creating your own radiation environment just by moving so fast. The psychological impact of this isolation can't be overstated. Human beings evolved in environments rich with sensory input, sounds, smells, textures, constantly changing visual landscapes. Even astronauts on the International Space Station can look down and see Earth, a vibrant blue marble reminding them of home. But in intergalactic space, there's nothing. No points of reference, no sense of motion except what your instruments tell you. Days would blend into weeks, weeks into years, with no change in the view outside. This sensory deprivation could be mentally devastating. Some mission planners have proposed using virtual reality to combat this. Crew members could spend time in simulated Earth environments, walking through forests, swimming in oceans, experiencing seasons and weather. But there's a danger here too. If the simulation is too convincing, people might prefer it to reality. Why deal with the monotony of the ship when you can live in a perfect digital paradise? You could end up with a crew that's physically aboard the ship, but mentally checked out, living entirely in virtual worlds. Maintaining the boundary between simulation and reality would be crucial. Another strategy is hibernation, which we touched on earlier. If we could safely put the crew to sleep for most of the journey, waking them only periodically to check systems or handle emergencies, the psychological burden would be greatly reduced. But even this has complications. Who decides when to wake people? What if there's a disagreement about whether a situation constitutes an emergency? And there's the haunting possibility that something could go wrong with the hibernation system, leaving some or all of the crew unable to wake up. The ship continuing on autopilot toward Andromeda with a cargo of frozen corpses. Let's shift gears and talk about communication. Assuming you wanted to stay in touch with Earth during your journey, you'd face increasing delays as the distance grew. Radio waves travel at the speed of light, so if you're 1 light-year away, any message you send takes 1 year to arrive, and any response takes another year to get back to you. By the time you're halfway to Andromeda, over 1 million light-years from Earth, the round-trip communication time would be over 2 million years. Conversations become impossible. You're essentially on your own. This communication delay has profound implications. You can't ask for help. You can't receive updated instructions or new scientific data that might be relevant to your mission. Any decisions you make have to be based on the knowledge you brought with you when you left. If humanity makes some breakthrough discovery that changes our understanding of physics or develops a faster propulsion system, you might never know. In fact, by the time you arrive at Andromeda, humanity might have already colonized it using technology developed long after you left, making your journey obsolete. This scenario, sometimes called the weight calculation, poses a real dilemma for long-duration space missions. If we launch a ship today that will take thousands of years to reach its destination, but we expect technology to improve such that a ship launched in 500 years could make the same journey in only 100 years, should we wait? The people on the first ship would arrive later than people on the second ship, despite leaving earlier. It's a paradox of progress, and there's no easy answer. Every generation might decide to wait for better technology, and as a result, no one ever leaves. But let's assume you do make the journey and you're now approaching Andromeda. As the galaxy grows larger in your view, you'd begin to detect individual structures. Radio telescopes on your ship would pick up emissions from pulsars, rapidly rotating neutron stars that sweep beams of radiation across space like cosmic lighthouses. Each pulsar has a unique rotation rate, a fingerprint that could be used for navigation. By timing the pulses from multiple pulsars and comparing them to predicted positions, you could determine your exact location, a technique called pulsar navigation that scientists are already developing for use in our solar system. You'd also detect other electromagnetic emissions. Andromeda, like all galaxies, contains regions of ionized hydrogen gas that emit radio waves at a specific frequency, 21 centimeters. This radiation allows astronomers to map the distribution of neutral hydrogen throughout the galaxy, revealing its structure even in regions too dark to see with optical telescopes. Your ship's instruments would create detailed maps of Andromeda's gas content, helping you identify safe routes through the galaxy and regions where new stars are forming. As you closed in, you'd need to make crucial decisions about where to go. Andromeda is enormous, and exploring the whole galaxy would take millions of years, even at light speed. You'd need to prioritize. Do you head for the central bulge, where stars are densest, but also oldest? Do you explore the spiral arms, where active star formation offers the possibility of young planetary systems? Or do you investigate one of the satellite galaxies, smaller and perhaps easier to survey comprehensively? One intriguing destination would be Andromeda's globular clusters. which we mentioned earlier, the galaxy has about 450 of these dense stellar collections, roughly twice as many as the Milky Way. Some are truly ancient, containing stars that formed when the universe was less than 1 billion years old. Studying these stars up close would give you direct access to cosmic history, allowing you to analyze the chemical composition of matter from the early universe, before many generations of stars had enriched it with heavy elements. But navigating near a globular cluster would be challenging. The stars are so densely packed that gravitational perturbations would be constant. Your ship's trajectory would need continuous adjustment to avoid being flung off course or, worse, pulled into a collision. And the radiation environment near the cluster's core, where stars interact frequently and stellar evolution proceeds rapidly, could be intense. You'd need to approach cautiously, perhaps deploying smaller probes to investigate while your main ship remained at a safe distance. Another fascinating target would be Andromeda's star-forming regions. The galaxy creates new stars at a rate of roughly 1 solar mass per year, meaning that every year enough matter condenses to form a star like our Sun. This might not sound like much, but over millions of years, it adds up to billions of new stars. These birth regions are where you'd find the youngest, hottest stars, as well as protoplanetary disks where planets are currently forming. If you wanted to search for habitable worlds, newly formed systems might be your best bet, though you'd have to wait millions of years for planets to cool and stabilize. Observing planet formation in real time, or at least on timescales of years rather than millions of years, would revolutionize our understanding of how solar systems develop. We've learned a lot from studying our own solar system and from detecting exoplanets around nearby stars in the Milky Way, but actually watching the process unfold in a different galaxy would provide invaluable comparative data. Are planetary systems in Andromeda similar to those in the Milky Way? Do they follow the same patterns, or does the different chemical composition and stellar density lead to variations? One thing we've learned from exoplanet discoveries in our own galaxy is that planetary systems are incredibly diverse. We've found hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. We've found super-Earths, rocky planets larger than Earth but smaller than Neptune. We've found systems with multiple planets in resonant orbits, where their orbital periods are related by simple ratios. And we've found rogue planets, worlds ejected from their home systems and wandering through space alone. Andromeda likely harbors similar diversity and perhaps configurations we haven't imagined yet. The search for life would undoubtedly be a priority. Even if you didn't find intelligent civilizations broadcasting radio signals, you might detect biosignatures, chemical indicators of biological activity. On Earth, life has profoundly altered the atmosphere. Oxygen, which makes up 21% of our air, is almost entirely produced by photosynthetic organisms. Without life constantly replenishing it, oxygen would react with rocks and disappear. Similarly, methane in Earth's atmosphere comes largely from biological sources. If you could analyze the atmospheres of planets in Andromeda, unusual chemical compositions might hint at life. Recent advances in spectroscopy, the analysis of light to determine chemical composition, have made this possible even from Earth for some nearby exoplanets. When a planet passes in front of its star, starlight filters through the planet's atmosphere, and different molecules absorb specific wavelengths. By carefully analyzing this light, we can identify water vapor, carbon dioxide, methane, and other compounds. Doing this from within Andromeda, much closer to the target planets, would be far easier and more detailed. But even if you found life, even microbial life, the implications would be staggering. It would answer one of humanity's oldest questions: are we alone? The answer would be no. Life exists elsewhere. And if it arose independently in Andromeda, separate from Earth's biosphere, it would suggest that life is a common outcome when conditions are right. The universe might be teeming with life, from simple bacteria to complex ecosystems, perhaps even civilizations far older and more advanced than ours. If we discovered life in Andromeda, the next question would be, what does it look like? Life on Earth shares a common ancestor. Every organism, from bacteria to blue whales, uses the same genetic code, the same basic biochemistry. DNA stores information, RNA helps translate it, and proteins do the work of the cell. But life in Andromeda might have evolved completely differently. It could use different molecules, different chemical processes, perhaps even different fundamental building blocks. Some scientists speculate about alternative biochemistries. Silicon is chemically similar to carbon and sits right below it on the periodic table. Could silicon-based life exist? The challenge is that silicon forms weaker bonds than carbon and doesn't create the same diversity of complex molecules. On Earth, carbon forms stable chains and rings that enable the intricate chemistry of life. Silicon compounds tend to be more rigid and less versatile. But in different temperature ranges or chemical environments, silicon might work. We simply don't know because we only have one example of life, Earth. Then there's the question of solvents. Life on Earth depends on liquid water. Water is an excellent solvent, meaning it dissolves many substances, allowing chemical reactions to occur. But other liquids might work in different environments. Ammonia remains liquid at lower temperatures than water. Methane and ethane are liquid on Titan, Saturn's largest moon, where lakes and seas of hydrocarbons exist. Could life evolve using these liquids instead of water? It's possible, though such life would be very different from anything we know. Finding genuinely alien life, life with a completely different chemical basis, would fundamentally transform biology. Currently, biology is the study of Earth life. But if we found a second, independent origin of life, biology would become a universal science, studying the general principles that govern living systems anywhere in the universe. We could begin to answer questions like, is DNA inevitable or just one solution among many? Are cells necessary, or could life exist as networks of chemical reactions without clear boundaries? Does evolution by natural selection apply everywhere? Or are there other mechanisms? But let's consider an even more exciting possibility. What if we found intelligent life in Andromeda? Not just microbes or simple organisms, but civilizations capable of technology, science, art, and philosophy. The implications would be profound and challenging. How would we communicate? If they're biological, their sensory systems might be completely different from ours. They might communicate through chemical signals, patterns of light, electromagnetic fields, or methods we haven't conceived of. Even if they use sound or visual signals like we do, we'd face the challenge of establishing common ground. Mathematics is often proposed as a universal language. The ratio of a circle's circumference to its diameter, pi, is the same everywhere in the universe. Prime numbers are prime regardless of who's counting them. We could potentially build communication through shared mathematical concepts, gradually building up to more complex ideas. But there's a darker possibility that we need to consider. When civilizations on Earth with vastly different technological levels have encountered each other, the results have often been catastrophic for the less advanced group. European contact with indigenous peoples in the Americas, Australia, and elsewhere led to disease, exploitation, and cultural destruction. If we encountered an alien civilization far more advanced than us, would we face similar dangers? Or conversely, if we were the more advanced civilization, would we have ethical obligations? These questions aren't just philosophical speculation. They have practical implications for how we conduct searches for extraterrestrial intelligence. Some scientists, including the late Stephen Hawking, have cautioned against actively transmitting signals into space, fearing that attracting the attention of advanced aliens could be dangerous. Others argue that any civilization capable of reaching us across Interstellar distances would be so advanced that we'd have nothing they'd want to take by force. Resources like minerals and energy are abundant in space. Why conquer inhabited worlds when you could harvest asteroids and lifeless planets without resistance? There's also the Fermi paradox to consider, named after physicist Enrico Fermi, who asked, "Where is everybody?" If intelligent life is common, and if at least some civilizations develop the capability for interstellar travel, then why haven't we seen any evidence of them? The galaxy is billions of years old, plenty of time for civilizations to arise and spread. Yet we see no signs of alien megastructures, no radio signals that are obviously artificial, no probe visiting our solar system. The silence is puzzling. Many solutions to the Fermi paradox have been proposed. Perhaps intelligent life is extremely rare, and we're one of the first. Perhaps civilizations tend to destroy themselves through war, environmental collapse, or other catastrophes before they become spacefaring. Perhaps advanced civilizations deliberately hide, following some kind of cosmic prime directive that prevents them from interfering with younger species. Or perhaps they're out there but using communication methods we haven't discovered yet, and our searches are like someone trying to detect radio signals using only smoke signals. Another possibility is the Great Filter, the idea that there's some barrier, some extremely difficult step in the evolution from simple chemistry to spacefaring civilization that very few species overcome. The filter could be behind us, something like the origin of life itself, or the evolution of complex cells which happened only once on Earth, despite billions of years of microbial life. If the filter is behind us, we're incredibly fortunate to have passed it. But the filter could also be ahead of us, some challenge that most civilizations fail to overcome. This is a sobering thought. It might mean that becoming a multiplanetary or multigalactic species is far harder than we imagine. As you explored Andromeda, searching for signs of life or intelligence, you'd also be conducting astrophysics research that would be impossible from Earth. Being inside a galaxy gives you perspectives we can't achieve from outside. You could map the three-dimensional structure of spiral arms, study the dynamics of star formation from within molecular clouds, observe supernovae from relatively close range, and investigate the central black hole without the interference of all the intervening stars and dust that obscure our view from the Milky Way. That central supermassive black hole deserves special attention. As we mentioned, it's roughly 140 million times the mass of the Sun, far more massive than Sagittarius A star in our galaxy. Black holes this large don't form from a single collapsing star. They grow over billions of years, accreting matter from their surroundings and merging with other black holes. The growth history of a supermassive black hole tells us about the galaxy's history, about how much gas was available, how many mergers occurred, and how active the galactic center has been over cosmic time. Some supermassive black holes are actively feeding, pulling in gas and dust that forms a swirling accretion disk. As matter spirals inward, friction heats it to millions of degrees, causing it to emit intense radiation across the spectrum from radio waves to X-rays. These active galactic nuclei can outshine all the stars in their host galaxy combined. Jets of particles traveling at nearly light speed can shoot out from the poles, extending for thousands of light years into space. Andromeda's black hole appears to be relatively quiet right now, but it might have been active in the past, and it could become active again if it encounters a fresh supply of matter. Approaching a supermassive black hole, even a quiet one, would be an experience beyond anything we can fully convey with words. As you got closer, space-time curvature would become noticeable. Clocks would run slower compared to clocks farther away, an effect called gravitational time dilation. Light from the stars behind the black hole would be bent around it, creating multiple distorted images. If you were close enough, you might see gravitational lensing effects where the black hole's gravity bends light from background objects, creating arcs and rings of distorted starlight. The event horizon, the boundary beyond which nothing can escape, would appear as a dark sphere silhouetted against the background stars. This is the black hole's shadow, and we've actually imaged one for the first time in 2019 when the Event Horizon Telescope collaboration released a picture of the supermassive black hole at the center of the galaxy Messier 87. That black hole is about 6.5 billion solar masses, even larger than Andromeda's, and the image showed the glowing accretion disk surrounding the dark shadow. Seeing something similar in Andromeda from much closer would be breathtaking. But you'd need to be extremely careful. The tidal forces near a black hole are enormous. Tidal forces occur because gravity gets stronger as you get closer to a massive object. Your feet, if they're closer to the black hole than your head, would experience stronger gravity and be pulled harder. Near a supermassive black hole, you'd eventually reach a point where the difference in gravitational pull between your head and feet would be strong enough to tear you apart, a process gruesomely called spaghettification. For Andromeda's black hole, this would happen well before you cross the event horizon. Interestingly, the tidal forces at the event horizon depend on the black hole's mass. For stellar mass black holes formed from collapsing stars, the tidal forces at the horizon are enormous, and you'd be spaghettified before crossing it. But for supermassive black holes like the one in Andromeda, the horizon is so large and far from the singularity that tidal forces at the horizon itself are actually survivable. In principle, you could cross the horizon of a supermassive black hole and not immediately notice anything wrong. Of course, you still couldn't escape, and you'd eventually reach the singularity where the laws of physics as we know them break down. What happens at the singularity is one of the great unsolved problems in physics. General relativity predicts that matter is crushed to infinite density, but we know this can't be the complete picture because infinities in physics usually signal that our theories are incomplete. Quantum mechanics, which governs the behavior of matter at the smallest scales, must play a role, but we don't yet have a working theory of quantum gravity that successfully merges quantum mechanics and general relativity. Solving this problem might reveal what really happens inside black holes. Some speculative theories suggest that singularities might not exist at all. Instead, quantum effects might halt the collapse before infinite density is reached, perhaps creating some kind of quantum structure we don't yet understand. Other theories propose that black holes could be connected to other regions of space-time, possibly even other universes through structures called Einstein-Rosen bridges or wormholes. These ideas are highly speculative and not supported by direct evidence, but they illustrate how much we still have to learn. Exploring Andromeda would also give you the opportunity to study stellar evolution up close. Stars are born, live, and die on timescales ranging from millions to trillions of years, far longer than human lifetimes. But in a galaxy with over 1 trillion stars at various life stages, you could observe examples of every phase. You could watch protostars emerging from their cocoons of gas and dust. You could study main sequence stars at different masses and temperatures. You could observe red giants shedding their outer layers, creating beautiful planetary nebulae. You could even arrive shortly after a supernova and witness the expanding debris field, rich with newly created elements. These observations would refine our models of stellar evolution. While we have good theoretical understanding based on physics and observations from our own galaxy, having detailed close-up data from a completely different galactic environment would test whether our models are truly universal or whether there are variations we haven't accounted for. The metallicity, the abundance of elements heavier than hydrogen and helium, affects how stars form and evolve. Andromeda's metallicity might differ from the Milky Way's, leading to subtle differences in stellar behavior. You could also study exotic objects like magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. These objects occasionally emit giant flares of energy that can be detected across millions of light years. Or you could investigate X-ray binaries, systems where a normal star orbits a neutron star or black hole, and matter from the normal star is pulled onto the compact object, emitting intense X-rays. Each of these objects offers a natural laboratory for studying physics under extreme conditions impossible to replicate on Earth. As we continue deeper into what you might discover in Andromeda, let's turn our attention to something that might seem mundane, but is actually crucial: dust. Interstellar dust grains are tiny, typically less than a micrometer across, smaller than the width of a human hair. They're made of various materials: silicates, carbon compounds, water ice, depending on where and how they formed. These grains might seem insignificant, but they play vital roles in galactic ecology. First, dust grains absorb and scatter starlight, affecting what we can see. Dense dust clouds can completely obscure regions of a galaxy in visible light, which is why infrared telescopes like James Webb are so valuable. Infrared light penetrates dust more easily, but dust doesn't just block light, it also absorbs energy and re-emits it at longer wavelengths. This means dust grains can heat up from absorbing ultraviolet and visible light from stars, then radiate that energy as infrared light. Mapping this infrared glow reveals where dust is concentrated and how much energy is being absorbed. Second, and perhaps more importantly, dust grains serve as catalysts for chemical reactions. In the freezing vacuum of space, many molecules form on the surfaces of dust grains rather than through gas phase collisions. Water, for example, can form when hydrogen atoms land on a cold dust grain and meet oxygen atoms. The grain provides a surface where atoms can stick and move around until they encounter reaction partners. Without dust, the chemistry of space would be completely different, and complex organic molecules might never form. These organic molecules are particularly interesting. Astronomers have detected over 200 different molecules in interstellar space, including formaldehyde, methanol, ethanol, and even amino acids, the building blocks of proteins. Some of these molecules are quite complex, with chains of carbon atoms linked together. The discovery of these compounds in space suggests that the chemical ingredients for life might be common throughout the universe, not just on Earth. If you analyze dust and gas in Andromeda, you'd likely find similar organic chemistry, perhaps with variations depending on local conditions. Dust grains also serve as the seeds for planet formation. In protoplanetary disks around young stars, dust grains collide and stick together, gradually growing from microscopic particles to pebbles, then boulders, then kilometer-sized planetesimals, and eventually planets. Understanding dust composition and behavior is essential for understanding how planetary systems form. By studying dust in Andromeda's star-forming regions, you could compare planet formation processes across different galactic environments. Now let's think about the timescales involved in your exploration. Even if you could travel at the speed of light, which, as we've discussed, is impossible for objects with mass, it would take 200,000 years just to cross Andromeda from one side to the other. The galaxy is simply too vast for comprehensive exploration on human timescales. You'd need to be strategic, focusing on the most scientifically valuable targets and using autonomous probes to multiply your presence. Imagine deploying thousands or millions of self-replicating probes, sometimes called von Neumann probes, after mathematician John von Neumann, who studied self-replicating systems. Each probe could explore a region of space, gather data, and then build copies of itself from local materials before moving on. Over time, these probes could spread throughout the entire galaxy, creating a comprehensive survey that no single ship could achieve. The data they collected would be transmitted back to a central hub, gradually building a complete picture of Andromeda. Of course, self-replicating machines raise concerns. What if they malfunction and replicate out of control, consuming all available resources in a runaway process? This scenario, sometimes called the grey goo problem in the context of nanotechnology, would need safeguards. Perhaps each probe would have a built-in limit on how many copies it can make, or require authorization from a central controller before replicating. The engineering and ethical challenges are substantial, but the payoff would be unprecedented knowledge of an entire galaxy. While your probes fanned out across Andromeda, you might establish a base of operations. Where would you set up such a base? A planet would be the obvious choice, but finding a suitable one might take time. You'd want a world with reasonable gravity, not so strong that it's exhausting to move around, but strong enough to hold an atmosphere and feel somewhat like home. You'd want a stable climate, a lack of extreme hazards like constant volcanism or severe radiation, and ideally, some useful resources like water and minerals. If you couldn't find a suitable planet quickly, you might consider building an artificial habitat. Space stations could be constructed from materials mined from asteroids or moons. The design could follow concepts developed decades ago on Earth, like the O'Neill cylinder, a rotating habitat that creates artificial gravity through centrifugal force. A cylinder several kilometers long and wide, rotating to simulate Earth gravity on its inner surface, could house thousands or even millions of people, complete with parks, cities, and artificial landscapes. One advantage of artificial habitats is that you can design them exactly to your specifications. You're not limited by whatever planets happen to exist. You can control the gravity, the atmosphere, the amount of sunlight, everything. You could create multiple habitats with different conditions, some Earth-like, others optimized for different purposes like zero-gravity research or extreme environment studies. Over time, you could build an entire civilization in space, independent of planets. This brings us to a fascinating concept. What if we didn't think of galaxies as places to visit, but as places to eventually live and spread throughout? Rather than sending a single expedition to Andromeda and then returning home, what if humanity, or our descendants, gradually migrated across the cosmos, establishing settlements on countless worlds and in countless habitats? Over millions of years, our species could spread from the Milky Way to Andromeda, then to other galaxies in the local group, eventually inhabiting a vast region of space. This scenario raises questions about identity and evolution. Would people living in Andromeda millions of years from now still be recognizably human? Evolution would continue and different environments would exert different selective pressures. Populations isolated from each other for long enough would diverge, potentially becoming separate species. And that's assuming only natural evolution. If genetic engineering and cybernetic enhancement become common, deliberate modifications could accelerate the diversification. You might end up with countless varieties of human descendants, each adapted to their specific environment. Some might be modified for high-gravity worlds with denser bones and stronger muscles. Others might be adapted for low-gravity or zero-gravity environments with elongated bodies and enhanced spatial awareness. Some might incorporate technologies directly into their biology, blurring the line between organism and machine. The concept of human would become much broader and more diverse than it is today. This diversity would be a strength. Different challenges require different solutions, and having a variety of forms and capabilities would make our descendants more resilient and adaptable. But it would also raise philosophical questions. At what point does something stop being human if consciousness can be uploaded into machines or distributed across networks, if bodies can be radically altered or replaced entirely? What defines us? Is it our DNA, our physical form, our consciousness, our culture, our history? These aren't just abstract philosophical musings. They have practical implications for how we think about long-term space exploration and the future of our species. If we're going to spread across the galaxy and beyond, we need to accept that change is inevitable and embrace it rather than fighting to preserve some idealized version of humanity as it exists today. The humans, or post-humans, who eventually explore Andromeda might be very different from us, and that's okay. They'd still be our descendants, our legacy, carrying forward the curiosity and drive to explore that has always characterized our species. Let's shift perspective again and think about what the collision between the Milky Way and Andromeda will actually look like. We mentioned earlier that it's going to happen in about 4 billion years. As the galaxies approach, their mutual gravitational attraction will accelerate them toward each other. From a vantage point outside both galaxies, you'd see two enormous spirals closing in, initially slowly, then faster and faster. The first close passage might not result in an immediate merger. Instead, the galaxies might swing past each other like two dancers in an elaborate cosmic ballet. As they do, gravitational forces would distort their shapes, pulling out long tidal tails of stars and gas. These tails can stretch for hundreds of thousands of light years, thin streamers of matter connecting the two galaxies. You've probably seen images of interacting galaxies with these dramatic structures. The Milky Way and Andromeda will create similar features. After the first passage, the galaxies wouldn't escape each other's gravity. They'd slow down, stop, and fall back together for another encounter. This process might repeat several times over hundreds of millions of years, each passage distorting the galaxies further, pumping energy into the stars' orbits and stirring the gas. Eventually, the galaxies would lose enough energy to friction and gravitational interactions that they'd settle into a single, merged system. The final product wouldn't be a spiral galaxy. Simulations show that major mergers between spiral galaxies typically produce elliptical galaxies, collections of stars with random orbits rather than the organized rotation of spirals. The new galaxy, sometimes informally called Milkomeda or Milkdromeda, would be a giant elliptical containing all the stars from both the Milky Way and Andromeda, well over 1 trillion stars in total. But here's the remarkable thing. Despite the chaos on a galactic scale, individual stars rarely collide. Space between stars is so vast that even when two galaxies merge, the stars mostly pass by each other like two clouds of gnats interpenetrating. The average distance between stars in our galactic neighborhood is about 4 light years. Stars are tiny compared to that distance, so the probability of direct collision is extremely low. However, the gravitational disruption would be significant. Stars would be flung into new orbits. Some would be ejected from the merged galaxy entirely, becoming intergalactic wanderers. Planetary systems could be destabilized, with planets thrown out of their orbits or sent careening into their suns. The Sun, if it still exists in 4 billion years, would likely survive the merger but might end up in a completely different part of the merged galaxy, far from its starting position. 4 billion years is a long time, long enough that the Sun will have evolved considerably. It's currently about 4.6 billion years old and about halfway through its main sequence lifetime. In another 5 billion years or so, it will exhaust the hydrogen in its core and begin to evolve into a red giant. The core will contract and heat up while the outer layers expand enormously. The Sun will grow so large that it will likely engulf Mercury and Venus, and possibly Earth as well. So when the Milky Way and Andromeda collide, Earth might already be gone, consumed by the dying Sun. But if somehow Earth survives, perhaps having migrated to a more distant orbit due to the Sun losing mass, the view from our planet during the merger would be spectacular. Andromeda, currently a faint smudge, would grow larger and brighter over millions of years until it dominated the sky. Eventually, you wouldn't see it as a separate object anymore. You'd be inside the combined system, surrounded by stars from both galaxies. The night sky would be dramatically different. Instead of a few thousand stars visible to the naked eye, as we see now, you might see hundreds of thousands or even millions, depending on where the sun ended up in the merged galaxy. The sky would be crowded with stars, many bright enough to cast shadows. There would be no darkness, only a perpetual twilight from starlight. It would be beautiful, alien, and perhaps a bit unsettling to anyone used to Earth's current night sky.